Today we are going to study about PN junction diode and its IV characteristics. If we join a piece of p-type semiconducting material with the n-type semiconductor such that a crystal structure remains continuous at the boundary as shown in the figure. So a PN junction diode consists of a PN junction formed either in germanium or silicon crystal. The diode has two terminals named as anode and cathode. The anode refers to the p-type region and cathode refers to the n-type region. So the arrowhead shown in the figure in the symbol points the direction of current flow when it is forward biased. So it may be noted that it is the same direction in which the movement of holes takes place. So the commercially available diodes usually have same notations to identify the P and N terminals. So the standard notation consists of type numbers preceded by IN or IN240 or IN1250 like that. So in some diodes, the schematic symbol of a diode is painted or color dots are marked on both the devices. Okay, so there are three types of diodes are available in the market. That is low current diode and current and small. These type of diodes are smaller in size, and second one is high current diodes. It is in larger size, and medium current diodes. So there are three kinds of diodes are available. Next, we will discuss about the IV characteristics of PN junction diode. Here, the forward biased junction junction diode circuit is shown here. This is the IV characteristics of PN junction diode. So let us see how the PN junction diode conducts current when it is forward biased. See, the positive terminal of a battery is connected to the anode of the diode and the negative terminal of the cathode. So hence the diode is forward biased. Let us gradually increase the voltage in small steps of about 0.1 volt and record the corresponding values of diode current. Now if the plot the graph with voltage across the diode along the horizontal axis and diode current along the vertical axis. So we shall obtain a curve like OAB. So the curve OAB is called as the forward characteristics of silicon PN junction diode. See, a careful study of the forward characteristics indicates that there is no diode current till the point B. Okay, so that it is because of fact that the external voltage is being opposed by the junction voltage, whose value is 0.7 volt for silicon and 0.3 volt for germanium. So however, as the voltage is increased above that the point A, the diode current increases rapidly. The point B, the diode current increases rapidly. It has been observed that a voltage of about 1 volt produces a forward current of about 20 to 50 milliampere. So the applied voltage should not be increased beyond a certain safe limit. Otherwise, the diode is likely to be burned out. So the voltage at which the diode starts conducting is called as knee voltage or cut-in voltage or threshold voltage. So the knee voltage is designated either by Vk or Vg. Its value is equal to 0.6 volt for silicon and 0.2 volt for germanium. So the knee voltage may be obtained from the forward characteristics by extending the curve AB backwards till it meets the horizontal axis. So the value of the horizontal axis is equal to the knee voltage. Next we will discuss about the reverse characteristics of PN junction diode. So the negative terminal of the voltage source is connected to the anode of a diode and positive terminal to the cathode. Hence the diode is reverse biased. The applied reverse voltage is gradually increased above zero in suitable steps and the values of diode are noted at each step. Now if we plot the graph with reverse voltage along the horizontal axis and the diode current along the vertical axis. So we obtain a curve marked as OCD. So the curve OCD is called as reverse characteristics of the PN junction diode. See, a careful study of the reverse characteristics indicates that when the applied reverse voltage is below the breakdown voltage, the diode current is small and remains constant value. So this value of current is called as reverse saturation current, that is I0. So it is of the order of nanoamperes for silicon diode and in the range of microamperes for germanium diode. So when the reverse voltage is increased to a sufficient large value, what will happen? The diode reverse current increases as rapidly. So the curve is shown in the figure is CD. So the applied reverse voltage at which